Good morning, grade 10s. So today we're going to go through properties of waves. So I need you to go to page 13 of your booklets. We're going to go through all the definitions, all the concepts. I am sitting outside, so if you hear some barking or some noise, I do apologize. You will see at the top of page 13 there's a block. That block is a block for all the definitions. So as we go through each concept, make sure you fill in the block there. Then if you go down further the page, you will see that there is a little section for each concept, and that section, you guys, it's your responsibility to fill in a summary of each physical concept. That is your job. So based on what I have said and what is on the slides, you are going to fill in what you deem is important for a summary or important for a description of the actual concept, and the picture should help you. So just follow along and use your deductive reasoning skills. Okay, so at the top of page 13, you will see there's a nice description there. It says that in addition to frequency, period, and the wave equation, we are going to look at the different properties of waves. In essence, we will be learning how waves behave in different scenarios. So grade 10s, please fill that in. A change in medium density, please underline that or highlight that. A change in medium density, a change in depth, or an obstacle can redirect the direction of wave movement as well as wavelength and speed. So we're going to see how these changes actually affect wavelength and speed. In majority of the cases, it does not impact frequency whatsoever. So I don't want you to even think about frequency and period. I just want you to think about how does this affect wavelength and speed. And what is speed again? Speed is velocity. Well, we use the term speed and velocity interchangeably. Typically speaking, speed is going to be distance over time, whereas velocity is going to be displacement over time. I covered this in the previous video, and I told you guys that those two terms kind of get muddled up quite a bit. Nonetheless, you're going to focus on how does this affect wavelength and speed. Okay. So the first concept that we're going to go through is reflection. Don't worry about filling in the definition just yet. I just want you to look at the bottom of page 13 and look at the pictures for reflection. So reflection basically means surface interaction or barrier interaction with, it's as the wavelength or wavefront is traveling, how does it interact with that surface? How does it bounce off that surface? And that surface interaction is going to result in a change of direction. So I've put a few pictures up over here. The first one you can see, that is an orca whale. That is echolocation. So whales and dolphins and bats, they use reflection of sound waves to hunt their prey. So the sound waves from the whale's song are reflected in an echo and travel back to the whale. What is important there is you can see that the sound waves are moving towards the right, towards the fish. Can you see? And once they bounce off the fish, they travel back into the medium. It's not like they are going somewhere else. It's not like they've disappeared. They are still in the medium. The medium is the water. Look at the picture of the bat. The bat is transmitting that sound wave, and the reflected wave, notice very carefully, is that reflected wave is not traveling back at the same direction or in the same direction. It's traveling back at an angle because it all depends on how that sound wave hits that barrier or that surface. In this instance, it's an insect. Okay, other examples are, can you see that mountain is reflected in the lake? Its reflection is at a certain angle. It's not at the exact same direction or angle as the mountain. So the light is bouncing off the mountain's surface, the snow, and then it is being reflected to a certain angle. We call that the incident wave, okay, or incident ray, and we have the reflected ray, and we're going to get into all of that later. Other examples are why do diamonds sparkle the way that they do? Because of the degree of reflection in those different cuts of diamond. There's so many geometric shapes that it's reflected at a 24 average 24 degree angle. And then a very, very common one would be that of the wing mirror of a car. You can go outside now, go look at your parents' car, and you will see that there is a certain angle to the reflection. Okay, guys, so the next slide, we're going to go into the definition, and we're going to discuss it a little bit more. So, in that little box on page 13, you are going to write the definition of reflection, which is a change of direction of a wave so it returns into the medium it originated from. Remember when we were talking about the whales? Remember when we were talking about the bats? That wave, whether it's a sound wave, whether it's a water wave, is going to return back into the medium. So please write that definition in, and then you're going to look at the bottom of page 13 and you're going to fill in a little bit more about what reflection really is. So there are two pictures I've put here on the slide. The first picture is, this is my incident wave. The incident wave is approaching, it hits the barrier, and then it is reflected. There is a line that we put between the incident wave and the reflected wave. And that line, or you could just call it the perpendicular or the normal line. The perpendicular or the normal line. This divides the angle of incidence and the angle of reflection. So this represents my angle. I hope you guys can see my little highlighter. Let's try and get it here. This represents my angle of incidence, and this represents my angle of reflection. And the most important thing from the law of reflection is that the angle of incidence, that degree of angle, is going to be equal to the angle of reflection. And what you will see in this sort of situation here, this should be about 90 degrees. So you're looking at about 45 and 45. Another example or another graphic of this can be seen in this picture over here on the right-hand side. You have, these are called wave fronts that are approaching the barrier. They are approaching the barrier, they hit the barrier, and the reflected wave is reflecting at a 90 degrees angle. Okay, so at the bottom of the slide, you will see we've said the angle at which the waves approach the barrier will determine the angle in the direction of the wave. It will determine the change in the direction of the wave. However, the law of reflection is absolute. What does that mean? That it's never changed. It doesn't matter how that barrier is sitting. The waves will always reflect in such a way that the angle at which they approach the barrier equals the angle at which they reflect the barrier. Okay, so I hope this makes sense. We're going to carry on to the next slide. I think I've got some other pictures, but some more pictures there that I've pasted on the slide to give you a clearer idea of what's going to happen when waves hit curved surfaces. So these are some really cool pictures that help contextualize just what I've said about the straight and the curved surface. So let's look at the curved surface first. So let's look over here on this side of here where I've got the reflection of curved surfaces. So we just looked at straight now. What's going to happen here is going to be different. If this was straight, if this barrier was straight, then the reflection is going to be directly back into the medium, straight away black. It's not going to change at all. Okay, however, this is curved now. So these wave fronts are approaching this curved barrier. When they approach this changes the entire behavior of the wave. It is no longer straight. They are going to move inwards towards what we like to call a focal point. So the red arrows indicate how they are going to move towards a focal point. I wish we could actually do this in the lab, because the only way you guys are gonna totally get this, or you're gonna feel comfy with it at this stage, because you've just been introduced to it, is if you play with ripple tanks. So maybe we can organize some sort of like little prac afternoon when school reopens. Here we've got another example of here. I mean, we've gone through the plane wave reflection before, but here we've got a circular wave. The circular wave is hitting this barrier over here. Can you see how it's hitting over here, and then it gets pushed out towards this focal point and towards the end of the edge? I'm not going to ask you to describe this in detail yet. Like I really don't think that's fair. But the most important thing is you need to know that it is going to affect the barrier, the shape of the barrier, or morphology of the barrier is going to affect how the waves change in direction. Here we've got a plane wave reflection from a convex barrier. Can you see how it's moving there? And now all of a sudden we've got semicircular waves that are moving outwards. We've got a circular wave reflection from a concave barrier. They move towards this concave barrier over here. And now you have these wave fronts that are moving towards a focal front. I really hope this makes sense, grade 10s. We're going to move on now to the next property, which is refraction.